Here we shall try to establish a relation between DFT and Z transform. Now, as per the definition of direct Z transform, x of z is equal to n, which goes from minus infinity to infinity, x of n, z to the power minus n. This is quite renowned to all of you, I suppose. Let us mark it as equation 1. And the inverse discrete Fourier transform is x of n, which equals to 1 over n, summation, which goes from k equals to 0 to n minus 1, x of k e to the power j twice by kn over n, where n goes from 0 to n minus 1. This is our next equation. Let us mark it as equation 2. What we shall try to do is establish a relation between x of z and x of k, that is our primary target in this topic. So how to do so? First of all, we should substitute x of n substituted in equation 1. So x of z here will become summation, n goes from negative infinity to infinity, x of n is replaced with this large expression 1 over n summation k, which goes from 0 to n minus 1, x of k times e to the power j twice by kn over n. And of course, z to the power minus n. Now look closely. In the case of discrete Fourier transform, that is DFT, n goes from 0 to n minus 1, as mentioned over here. So what we can do is simply change the limit of n from negative infinity to infinity to the new limit 0 to n minus 1. Because all we are concerned, as I have said earlier, in case of discrete Fourier transform, is this limit 0 to n minus 1. So summing from negative infinity to infinity is bothersome and rather redundant, and we shall avoid it. So changing the limit, this becomes n goes from 0 to n minus 1, 1 over n. The rest of the equation remains same, x of k e to the power j twice by kn over n, which is multiplied by z raised to the power negative of n. Now once again, as per the property of summation, we will interchange the summation bits. 1 over n, since it is independent of either of them, we bring it out. 1 over n summation of k, which goes from 0 to n minus 1. X of k is also brought out of the second summation, since it is not dependent on small n. N goes from 0 to n minus 1. E to the power j twice by kn over n times z inverse n. Times z inverse n. Now this can be written as 1 over n summation, where k goes from 0 to n minus 1, x of k, this is capital X, summation e to the power j twice pi j twice pi k over n times z inverse 1, which is whole to the power of n. Just bringing this n term out of the individual expression. A simple property of exponents. The limit here, n goes from 0 to n minus 1. So, once again, this marked expression over here, let me mark it, is nothing but in the form of summation where a to the power n, and n goes from 0 to n minus 1, which is gives us the geometric progression formula a to the power n minus 1, a minus 1, where in our case a is equal to e to the power j twice pi k over n times z inverse 1, z inverse. So, expanding this bit, we get x of z to be equal to 1 over n summation k, which goes from 0 to n minus 1, x of k e to the power j twice pi k n z inverse whole to the power of n. So here it will be n instead of small n, minus 1 divided by e to the power j twice pi k over n z inverse minus 1. Now bringing this n inside of this expression, we get 1 over n summation x of k e to the power j twice pi k n over n z inverse n minus 1 e to the power, the denominator remains as it is, j to the power twice pi k over n times z inverse minus 1. The summation limit where k goes from 0 to n minus 1. Now this 2n cancels out and we are left with 1 over n summation where k goes from 0 to n minus 1 x of k e to the power j twice pi k I'm sorry, this bracket will be over here because z is not a part of e to the power of this exponent, z inverse n minus 1 e to the power j twice pi k over n z inverse minus 1. Now, I have told this hundreds of times, this expression is nothing but equal to 1. So, this numerator becomes 1 over n, where k goes from 0 to n minus 1, x of k z inverse n minus 1 over e to the power j twice pi k over n z inverse minus 1. Now, since the numerator is independent of the summation operator, we can bring it out and simply write as x of z to be equal to z to the power minus n minus 1 over n summation k, which goes from 0 to n minus 1, x of k e to the power j twice pi k over n z inverse minus 1. So simply this is our required expression that gives us a relationship between the Z transform and the discrete Fourier transform. So using this formula, if one of the transforms are given, it is quite easy to find out the other one, and it can be used in order to interchange between Z transform and discrete Fourier transform. So at this point, I think I should stop today's lecture. If there are any questions, I hope you shall ask it during the comment section, in the comment section of the Google Classroom. And I hope all of you are safe. And after a long Eid vacation, we meet once again. And all that is left to say is good luck, Godspeed, goodbye.